Hello. In this video, I'm going to talk about the theories of Rameau, especially his theory of the fundamental bass, as he described it in his 1737 book, Génération Harmonique. Before I get to that book in particular, I'm just going to give a very broad overview of his earlier version of the theory, which came from his 1722 Traité de l'Harmonie. So to that end, I'm going to now share my screen. Theorists and composers had known for a long time by 1722 about the invertibility of certain harmonies, especially the triad. For instance, if we have a triad consisting of the notes C, E, and G, we think of that as a C major triad now, although they would not necessarily have used those terms. But in continuo terms, this would be a chord on C with a figure of 5/3. Or you could just leave the figure out and these notes would be assumed. Well, I could rearrange those notes slightly. I could have a higher C on top, and this would be a chord on E with a figure of 6/3. And these two are basically very similar in sound because they share so many notes. And likewise, I could go further and arrange the notes like this, with the G on the bottom and C and E above, with a figure of 6/4, which in music generally happens at cadences. And then the 4, which would be treated as a dissonance since it occurs as a fourth above the bass, would resolve down to B. The E would likewise move down to D, and you would get a harmony on G. But notice that in all three cases, the musical materials are similar because they involve the same three notes. So the first chord, the second chord, and the third chord are somewhat akin to each other. And as we've discussed, guitarists and other theorists as well had noticed this connection by the beginning of the 17th century. What's new with Rameau is that he also applies this theory of invertibility to dissonant chords, including what we now call the dominant seventh chord. So you can take these notes, which are dissonant and would resolve to a C harmony. They would be a figure of seventh on G. You can rearrange them by putting the G on top, and then you get the figure of 6/5. This is the chord that occurs on the leading tone. In French, they would call this the chord of the false fifth. You can put the D on the bottom with a figure of 4/3, and in French they call this the chord of the small sixth. And lastly, you could have the F in the bass, and a figure of 4/2. And in French theory, they would call this the chord of the tritone because it has a tritone between the F in the bass and the B above it. So from Rameau's point of view, in the Traité de l'Harmonie, each of these is also basically interchangeable with the others because they all seem to have the same collection of notes. So the seventh on G, 6/5 on D, 6/5 on B, 4/3 on D, and 4/2 on F are all related in that they have dissonances that would then want to resolve to a C harmony. So how does that work? Which notes in that chord want to go where? Well, from Rameau's point of view, he names this note, the chord seventh, the minor dissonance. And he names this note, the chord third, as the major dissonance. They get that name because of the intervals in which they take part. So the minor dissonance is a minor third above the perfect harmony GBD, which would be the major triad. The major dissonance is the major third above the root. And for Rameau, the minor dissonance always goes down. And the major dissonance always goes up. And this single rule has two important characteristics. First, this explains the old traditional rule that sharp notes ascend and flat notes descend. This was a commonplace in Renaissance theory, including in Zarlino. And of course, in practice, it's not true at all in much 17th and 18th century music, because those musics are not concerned with the practice of musica ficta and the rules for those notes. But we're given this kind of authority from traditional theory that is then difficult to explain. So Rameau uses this to say, well, this is what Zarlino really meant. The minor dissonance in a dominant seventh chord goes down like a flat note, and the major dissonance goes up. And that accounts for that entire rule. So there's kind of a historical thing. The other nice thing about it is that in continuo practice, there were various rules for treating all the different notes of each of these chords. And in Rameau's theory, those rules are all elegantly explained by this single rule. So it greatly simplifies, from Rameau's point of view, continuo practice. Because if you have a seventh chord on G, you know that the major dissonance, the B, needs to go up to C, and the minor dissonance, the F, needs to go down to E. So as long as you do that, everything else will work out accordingly. Whereas you could also have the B in the bass, and then you get the minor dissonance, which is now the flat fifth above the bass, and the major dissonance is in the bass itself. So those are going to resolve down and up respectively, and that tells you how to treat the 6/5 chord, and so on and so forth. So this allows Rameau to simplify continuo practice and to do so in a way that has this kind of nice historical resonance with Zarlino's theories. And the way he would notate that is with the idea that each of these chords has a fundamental bass tone of G. And whichever way you're going to resolve these, they are going to move with a fundamental bass of G moving up to C. And that can actually have either C or E in the bass, or according to the theory, G, although in practice that never really happens. So all kind of voice leading is explained by this motion of the seventh chord, which Rameau calls the dominant, or the seventh chord that is on scale degree 5, which he calls, confusingly, the tonic dominant. You do need to know this term, which will then move to the tonic. Any seventh chord is a dominant of some kind. If it's a seventh chord on a different scale degree, it's not the tonic dominant, it's just a simple dominant. If it's a seventh chord on scale degree 5, which you might think of as Roman numeral 5, it's called the tonic dominant, or in French, dominant tonique. tonic, and that needs to go to the tonic, which is the perfect chord. So any seventh chord is a dominant in that sense, because the seventh is a dissonance that needs to resolve. And any perfect chord is a tonic in that sense, in that it's a perfect chord and is not in need of any particular resolution. So that's a sort of a crash course in Rameau's theory as it stood in the Traité de l'Harmonie. And in Génération Harmonique, he goes much further with his claims for the fundamental bass, essentially saying that, well, it turns out that the fundamental bass is an attribute of nature. It arises from the physics of sounding bodies. Therefore, it's contained in any musical vibration that occurs. And as a result, it's part of this natural generative process by which everything arises from this fundamental harmony and these harmonic progressions that Rameau describes. So obviously it's an extremely ambitious program, and the idea is that the fundamental bass is both a natural phenomenon and explains pretty much everything there is to explain in music. So Rameau couches this in prose that is kind of famously difficult to read and not the most well organized. So what I'm going to do in this video is try to explain the argumentation he lays out in Génération Harmonique for where the fundamental bass comes from and what it gives us. And what it gives us is everything in music, from the scales we use to the way we perceive pitches, to the tuning system we use, to the way harmonies sound when they are well composed. So fundamental bass really is kind of fundamental in that sense. So you may have thought of in the past of Rameau's theory of the fundamental bass as like just an idea of chord roots. And it is partially that, but it's not accurate to say that that's the extent of the fundamental bass theory, because it actually goes much further than that, in that it's about these progressions. So to begin with, Rameau establishes the natural occurrence of the fundamental bass using physical experiments. And to accomplish these experiments, he uses a variety of instruments, and I'm going to recreate a couple of them now for our purposes. So one of the ways Rameau demonstrates his theory in experimental terms, his theory that is that the perfect chord, the major chord, is essentially indistinguishable from the tone produced by a sounding body, is an old and traditional combination of stops on the organ that was widely used in France. And you have to remember, of course, that Rameau, before he became famous as an opera composer, was essentially a provincial organist. So if I take a fundamental tone and I play it on a normal stop, I can add to it certain other tones in a normal combination. So one of these would be the octave, and you can hear that I'm adding a second tone. Another of these would be the double octave, and then I would also traditionally add a stop that plays a 12th and a second stop that plays a 17th. On my organ, because it's a small organ, these are combined in a single stop. But here, if you can hear the addition of the two notes G and E. So you hear now the major chord. Now what Rameau points out is if you then do something else, like if you play a little brief prelude on a different stop,
and then you come back to that combination, you will now hear it as a single tone, because your ear has now, you're no longer thinking about the way individual stops were added. And because of that, you can even play chords on it. And it doesn't sound bad, even though the individual pitches included make quite a cacophony, because even the single chord, C, E, and G together, actually contain these pitches on the C, these pitches on the E, and these pitches on the G. So, you know, if you actually were to break those down into individual pitches, it would be quite shocking. But because of the way they're added, you don't hear it that way, especially once you've sort of erased that from your mind. And for Rameau, this proves the identity between the perfect chord, the major chord, and the individual tone of the sounding body.
A lot of the experiments in chapter 1 of Génération Harmonique are geared towards establishing the fact of upper and lower resonances. That is what we now think of as the overtone series, and what Rameau believed incorrectly was the undertone series. He used, for his experiments, viol and so forth. I'm just going to use a piano, and I meant to do this at church where I have a grand piano, but I'm just doing it at home on my crummy upright. But I hope you can still hear the important things. So a lot of this is probably stuff you've already done, but it's worth sort of reviewing, because to Rameau, this was kind of like earth-shattering and interesting. So the first thing is that in any fundamental tone, there are sympathetic vibrations that occur at the upper 12th and at the upper 17th, which is 2 octaves and a third. So for instance, to get the 12th, if I hold down this G, and then I'm going to strike the C a 12th below it, and then when I let go, you'll hear the upper G ringing, which means that the G string of the piano is vibrating sympathetically with the G, which is contained in the fundamental vibration of the C. So in a sense, the G is part of the C, or it's generated from the C, as Rameau would have had it. So you can hear this note, right? It's faint, but I'm going to do it one more time. Now I can do the same thing at the upper 17th. So this is this E up here. And again, this is like the 5th harmonic in the harmonic series. So the G is the 3rd harmonic and the E is the 5th harmonic. So if I hold down the E and I strike the C, you should hear the E ringing. So be listening for this note. I'll do it again. Okay, so this establishes that the upper 12th and the upper 17th are part of the fundamental vibration. And when a body sounds, a sounding body as Rameau has it, those notes are contained within the fundamental tone. And of course they give the major triad in this kind of spread out form. So that's the way in which harmony, through the form of the major triad, is generated from the single tone, just by the nature of acoustic vibration.
Well, what about the other way? Rameau believed that there were vibrations that were multiples of the kind of idealized string length. So if I have a string that's the C, the G up here will be, if all other factors of the string are equal, then this string will be 1/3 of the length of this one, whereas the E will be 1/5 of the length of this string. Well, there's also sympathetic vibration that occurs in strings that are greater than the original length. So, and we can also establish this experimentally at the piano. So if I hold down that same, or if I want to get that E and imagine it generating tones downward in what some later theorists and physicists in the 19th century thought of as the undertone series, well, I could go down a 12th to the A. So I can do the same thing I did before. I'll hold down the A without striking it so that the string is, free of damper. And then I'm going to strike the high E, and then when I let go, you should hear the high E still ringing because it's being sounded as an upper harmonic of the A string. Right, so that's a perfect 12th below, A to E. I can also go a major 17th below, and this time I get C. And the same thing should happen. And indeed it does. So what Rameau noticed correctly was that when a string is vibrating, the strings a 12th and a 17th below will also be seen visibly to vibrate sympathetically. The problem for Rameau is that he erred a little bit when he said that the E causes the A and the C to vibrate. That's not exactly true. It causes the A and the C to vibrate partially. It causes the A to vibrate as though you had plucked its third harmonic, and the C to vibrate as though you had plucked its fifth harmonic. So Rameau got a little bit raked over the coals later in the 18th century for his sort of bad physics, because he thought that this note was sort of generating these lower pitches, when of course that's not actually correct. But that doesn't really negate his theory necessarily, because it's still a fact that these are related in that this tone, which Rameau thinks of as the generator, is contained in some sense in both of these notes. And notice what harmony that gives. C, A, and E, or if I rearrange them by octave, A, C, E. So Rameau generates the minor triad downwards in this book. He struggled over the course of his career with different ways of generating the minor triad, but this was the one he settled on in Génération Harmonique. So the minor triad results from the lower resonances, or that is sympathetic vibrations with imaginary strings that are perfect multiples of the original string, whereas the major triad is generated from the upper resonances, that is sympathetic vibrations on strings that are perfect fractional divisions of the original string. In particular, 1/3 giving the upper 12th or the perfect fifth, and 1/5 giving the upper third or major 17th.
So why all this emphasis on physical experiment in Génération, and why that in distinction to the earlier practice in Traité de l'harmonie? You have to situate Rameau's thinking in the scientific, musical, philosophical thinking of his time. As with a lot of historical music theory, theory and theorizing about music had a lot to do with broader intellectual trends, those of philosophy and intellectual life more generally. So Rameau, in trying to find a physical basis for his theories, is really acting in the manner of Descartes. You might be familiar with Descartes' Discourse on Method or Meditations on First Philosophy, where he basically rejects all received wisdom, all sort of handed down knowledge, and decides to fashion his intellectual system from first principles. So, of course, the principle on which Descartes founds his system is the "I think, therefore I am." Right? He he sort of rejects all given ideas and then forms his system based on the fact itself of thinking, on which he is able to sort of build his entire philosophy and so forth. Rameau is doing something similar in Génération. Namely, he's establishing that all of his beautiful theories of the fundamental base, that sort of the simple principles underlying the resolution of dissonance in musical practice, unlike his earlier views, they're not just based on practice or finding a convenient way to explain the practice. Rather, they arise from first principles. So the mission statement of the book is given at the beginning of chapter 2. He says, music is a physico-mathematical science. It's a science, right? It's not just a thing we do to play continuo. It has this basis in science, the science of the Enlightenment, the science like that, this is what, 40 years after Newton's Principia Mathematica or so. And Rameau is often compared, and was compared by his contemporaries with Newton for sort of recreating the musical system out of scientific foundations. Of course, as we saw with the undertones, he's maybe a little shaky on some of the science, but that's not necessarily a reason to throw out the whole system. So it's a physico-mathematical science. It combines physics, which has as its object sound or the tone. Any periodic vibration of anything will create a musical tone that we can then perceive as a pitch. And the mathematical object is the connections found between the different tones, the ratios found between them. Right? And what does music do? What is its end? Its sort of teleological cause? Well, it's to please us and excite in us diverse passions, right? I can't summarize the theory any better than that. It's a science with a physical object of sounds, a mathematical object of relations, numerical relations between the sounds. And its goal is to please and to move us with our passions. So now let's put a few numbers on Rameau's theory. Naturally, Rameau likes to start his book with the fundamental sound of C. So we'll begin there as well. Although, as we'll see, for reasons of simplifying mathematics, he will later move on to a fundamental of G, and we'll explain that when we get there. So in any tone, just take the tone C, that tone is not just a tone, it's a fundamental sound that contains within it other tones. The only two other tones that we're going to be concerned with are the 12th, namely G, and that Rameau will give the fundamental tone the number 1, and the G he will give a number of 1/3. Okay, and the reason is that if you had a string of length 1, it would give that C, and then if you would divide the string into thirds, it would give the G a 12th higher. okay? And then the other one we're going to be concerned with is the 17th, which is the 2 octaves and a major third. And that one is going to be given the number 1/5. So this progression, 1 to 1/3 to 1/5, happens to give us the perfect chord in that kind of nice spacing of, you know, C kind of low in the bass, and then G kind of alto-ish, and then E in the treble. Oh, sorry, I should have drawn a clef here. So notice we're dealing with fractions, and we're going to be getting rid of the fractions before long. And also the spacing is a little clunky because it's so spread out. It's nice acoustically, but musically it's a little weird. At the same time, we have to go the other way. So let's now take this upper C, and we'll call that 1. I'll explain in a little bit why both of these C's are 1. And if we were to triple the length, we would get the 12th below, which is this F. And then if we were to have a quintuple length string, we would get this low A flat here, right? And if you think back to our talks about tuning theory, or maybe other sort of Greek theory, you know, this one is harmonic, and this one is arithmetic. And those have to do with the way these progressions work. Harmonic has fractions, arithmetic does not. Rameau points out that the harmonic is more perfect because these vibrations are contained within the vibration of the fundamental string, whereas the arithmetic one, these vibrations are not contained within the vibration of the fundamental string. You need other strings tuned to these lower pitches, and they will vibrate sympathetically with this one. And as we saw before, of course, physically, they don't vibrate in their entirety, producing these actual pitches, F and A flat. They'll just both vibrate sympathetically to produce the C's that their fundamental sounds contain. And of course, Rameau went a little too far with the kind of physical argument there. All right, so these are the basic numbers we're going to be dealing with that we take as axiomatic. So we have this kind of basis for everything else, which is the sounding tone, the sounding body. And then that produces, in the harmonic direction, produces the major chord, the perfect chord, and in the arithmetic direction produces the minor chord. And the major is somewhat superior to the minor because its resonance is contained. Okay, well, how can we manipulate these numbers in order to make them work to our advantage more? Well, one other thing that Rameau is going to take for granted is octave equivalence. Now, he came into a little bit of controversy over this because not all theorists accept octave equivalence. Famously, Euler, who was a sometime correspondent of Rameau, disagreed with him on this point. And of course, it sort of is in some ways the basis of Rameau's theory, because he uses it to justify his whole idea of the fundamental base. Well, what does it mean mathematically? It means that any of these numbers for our purposes, can be doubled or halved. Right? So any note, like the C would be 1, while the C an octave higher would be half. And to get from 1 to 1/2, we just multiply by 1/2. And then this C up here would technically be 1/4, okay? Because we would multiply by half to get the middle C, and then we would multiply by half again to get this high C, and that would be, the same as 1/4. Likewise, if we were thinking of this C as 1, we could double it to get middle C, which would be 2, and then we could double that to get the low C, which would be 1. Well, basically, that means with octave equivalence that we treat any number and anytime it's multiplied by a power of 2 as basically equivalent in some sense or congruent. So 1, 2, 4, and 8 all represent C, as does 1/2, 1/4, 1/8. They're just C's in different octaves. But for Rameau's theory, they are each C. And so far, C is the fundamental sound, whereas G could be represented by 1/3, 2/3, 4/3, any sort of multiple of 3, right? So any multiple of 1/3. So you can double or halve anything you like at any time. So now let's do the operation that Rameau suggests. And for this, I'm going to look at his own musical example in a minute. But first, we're just going to show that the multiplication by 2 or by 1/2 can be just sort of done again and again to get the actual pitches that you want. So for instance, we could move the C up 2 octaves, right? That base C. We're going to look at this first example. And we're going to move it up 2 octaves. And so we'll call that 1/4, right? Because move it up 1 octave, and we get the high C, or we get middle C, and we move it up another octave, and we get the treble C. And then the G, we're going to have that as well, move it up to this G. And so, of course, that's going to be 1/6 because we've taken this G on the second line of the treble staff, and we've moved it up an octave to the G an octave higher. And so multiplying it or moving it up an octave is the same as multiplying by 1/2. 1/3 times 1/2 is 1/6. And then the E, we're just going to leave where it was. So we get 1/5. And now we get Rameau's harmonic progression that gives us the major chord, 1/4 to 1/5 to 1/6, which of course is a little nicer looking than 1 to 1/3 to 1/5. And these are equivalent. Okay, likewise, let's do the minor chord now. The C we are going to think of as 4. And again, I could write this in a really low octave, but I won't. It's just easier this way. The 3 for the F, we're just going to double and make that 6. And then the A flat, we're going to leave where it is as 5. And of course, you have to imagine this all taking place in the kind of bass range. So if if you'd rather think of it this way, it would be like a bass clef up here, and this would be giving you the C minor triad. Now, one little note here. The minor triad seems to be generated from the 5th of the chord. So we would call this an F minor chord, right? But it seems to be generated downwards from the C. So from a 19th century perspective of Ugo Riemann or other theorists like that, the true root or prime of the minor chord is the fifth. But Rameau, being a continuo player, did not go that far. He believed that the F is the fundamental tone of the minor chord, and so he rearranges this to give us F, A flat, C, and he writes that as 6, 5, 4. So now let's take a look at his examples where he shows this. All right, so here's Rameau's example of the harmonic progression: 1/4 to 1/5 to 1/6 and 1/8. And notice this bears a lot of resemblance to things we've seen before in Zarlino, where harmonic division of the octave gives you fifth plus fourth, and then harmonic division of the fifth gives you the major third, and then the minor third. So here you give C, E, G, and high C. And we've got the major third, the minor third, and the fifth. And then on the other side, the arithmetic side, we derive the minor chord arithmetically from the fundamental of 4, going down a major third to A flat, the fifth, the low fifth here, and then down a fifth also to the F, which with the minor third on the bottom. So this is Rameau's derivation of the minor chord in Génération Harmonique. So these are sort of two kind of fundamental examples, the first two examples, in fact, in the book. All right, so we've got now our two perfect chords, the major triad and the minor triad. And how are we going to connect them? Well, Rameau says that at this point, if he were basing his observations on musical practice, he would just sort of give us the scale, maybe the kind of rule of the octave, scale and the bass, and then we'd go from there. But the idea is that he's really working from first principles. So we don't have yet a way to move by step. Instead, what we have are the intervals we've generated, namely the octave, the perfect fifth, and the major third. And we have not generated any other intervals, right? Those are the kind of fundamental consonances. And in fact, we've already established that the octave is not really a progression at all. If you move from one note to its octave, you haven't moved to a new tone because for Rameau, octaves are essentially equivalent. So what if, working from first principles, we only allow progression of the fundamental tone by major third or by fifth? Let's take a look. So example 3 gives us a table that does exactly this. So we've got our generating tone, fundamental of C, and we can move by major third, which is sort of moving horizontally, and by perfect fifth, which is descending. Wait a minute, I thought that G was 1/3, and we had this sort of perfect chord is 1 to 1/3 to 1/5, or, with octave equivalents, 1/4 to 1/5 to 1/6. Well, Rameau points out, and you may have noticed this yourself, that the fractions and the whole numbers are just inversions of each other. There's no real need to use fractions anymore because the harmonic series moving in one direction and the arithmetic series moving the other are sort of perfect reflections of each other. So what Rameau does at this point is to just get rid of the fractions for ease of doing mathematics. So, and in fact, he says, well, we'll just use whole numbers now to talk about the harmonic direction. So now going from C to G, instead of thinking 1 to 1/3, we'll just say 1 to 3. And again, we've encountered this before, but there is a reciprocal relationship between the speed of vibration, that is like the harmonic frequency, and the length of the string, right? So before we were talking maybe about string lengths, and now we're talking about frequency, or however you want to think of it. So at this point, we just get rid of the fractions entirely, or we just sort of flip it over so that to talk about harmonic series, we'll just use whole numbers. And it's just for convenience sake, okay? So this table gives then pure fifths in the columns and pure major thirds in the horizontal direction, right? And we're going to use these to derive everything else we're going to be looking at in terms of the fundamental base. And so if we want to go by fifths, up a fifth, we multiply by 3, and we get from C to G. And then we could multiply that by 3 and get to D. And we can multiply that by 3 and get to A, and so forth. As you see, we're just, the columns are essentially just powers of 3. And the rows are powers of 5. So if we want to go up 1 major third, we would multiply by 5. We consider 5 interchangeable with the note E now. And we could go up to another major third to get G sharp, and that's going to be 25, etc. And then we could go up yet one more major third to B sharp, and that's going to be 125. Notice that 125, there's no way for this C to get to the place where the B sharp is just by doubling. I mean, you could see that right away, because if we keep doubling, we're going to have, a power of 2 and an even number. And with, and as you know, from, powers of 2, we could double and get to 128. We can't get to 125. So that difference is what Rameau calls the quarter tone, what other composers or theorists often call the diesis. But we'll use Rameau's terminology, or I'll try to remember to use Rameau's terminology. So that's about 40 cents or a bit more in modern terms. So it is like a half of a semitone or a quarter tone. And we can see other tuning discrepancies that are familiar to us on this table. So for instance, if we go up a series of fifths, C, G, D, A, E, we end up at an E that is 81, okay? But we also have the pure E, a pure major third above C, which is 5. And we could keep doubling 5 because of octave equivalence, 5, 10, 20, 40, 80. And then we get that discrepancy, which is the syntonic comma, 81 to 80. So there's your syntonic comma, which is, one thing that has sort of bedeviled just intonation since it was first proposed. One more tuning discrepancy. If you follow the cycle for 12 steps, you end up at this B sharp that is 531,441, which you may recognize as the numerator of the Pythagorean comma, right? This one is off from a pure C by some small amount, okay? Now, both of these commas, the syntonic comma that arises from this E, and the Pythagorean comma that arises from this B sharp and this C, are slightly different, but Rameau just calls them both commas, okay? So he's being a little inexact there. They are very, very close to each other. They're almost the same size in kind of sense terms. So, maybe he's just being a little kind of giving it a shorthand. And they are a smaller interval than this quarter tone, which is rather considerably more out of tune. These commas are like 24 cents or so, and this quarter tone is more like 40 something cents. So there's a bit more of a tuning discrepancy this way. Okay, well, let's figure out which of these is more perfect. Because we're going to derive some things from progression by these intervals, now that we've established that these are the intervals we could use. Well, we can see, this is, and now I'm kind of acting like Rameau here. We can see that the column giving the fifth is superior to the other direction because it contains all of the other tones. So the mi, or the E given by third, is contained in the fifths here. The G sharp is contained here. And the B sharp is contained at the end. Now, again, none of these are equivalent tones. This E is not the same as this E. This G sharp is not the same as this G sharp. And this B sharp is not the same as this B sharp. And that's just sort of part of the nature of just intonation. And of course, it's also, if you want to get kind of mathematical about it, it's just a consequence of the fundamental theorem of arithmetic, which we've known about for thousands of years, namely that any number can be uniquely factored into prime numbers. Well, this column has only factors of 3 because it is just powers of 3. This column has a factor of 5 and a bunch of 3s. And this column has 2 5s and a bunch of 3s, and so forth. Well, because of that, they're never going to be equivalent. It's not possible. So there's always going to be this kind of incommensurability between them. But Rameau uses this table to establish that fifths are sort of more fundamental than the others because they contain the others, right? And the other reason to give is that the fifth proceeds out of the string or the fundamental sound before the third does. So we're going to take the fifth as our kind of basic model of progression. Now, Rameau points out that if we move from a root to a fifth, which is what's shown here, each of those is in fact a fundamental sound. So here we've got C moving to G. There's our 1 to 3. You've got to sort of keep track of these numbers for Rameau. And he does everything he can to get rid of fractions and make it easier to think about his numbers, which is helpful. So we've got C and G. And of course, those are all going to contain, they're going to contain these harmonic sounds, which are in fact the overtones. So we've got the octave, which is 2. And of course, we can just basically get rid of that. The fifth, which is 3, and the third, which is 5. Okay, and then over here on G, we've got the octave G. So this is a French violin clef. The fifth D, which is going to be 9, and the B, the high B, which is going to be 15. Okay. Well, can we get any melody out of this? Yes, we can. The largest segment of scale that we can put together starts on B. So with the G as a fundamental base, so now this bottom line is basically a fundamental baseline. We've got G generating B above it, and we'll call that 15. The C generates, of course, a C above it, and we'll call this 16. You have to imagine, he's doing some octave reduction here, okay? Obviously, we earlier we were calling this one 4. You could imagine this 2 octaves higher, but it's not really necessary to do so. Then the G gave us the D, and then C gave us E. So we get this scale segment from B to C to D to E. Again, this is French violin clef. And that is, you may recognize it if you've studied Greek theory, this is the diatonic tetrachord of the ancient Greeks. A semitone on the bottom, and then 2 whole tones. And then this is the one that was called the syntonic diatonic, described by Ptolemy, and then again used by Zarlino, with a pure major third occurring between the second note here and the third note, so C to E, and then two different sizes of whole step, namely the major tone, as Rameau calls it. This is 16 to 18, or in reduced form, 8 to 9, and then the minor tone, which is 9 to 10. Okay, and these together come from this fundamental succession. We cannot go further than this, right? You can't go down to F because we don't have an F yet. And you can't go up to F because we don't have an F yet. F doesn't occur as a fundamental emanation of either of these tones. So this is sort of the limit of scale. And as Rameau points out, this was the way the Greeks thought about scale segments as well. And isn't that nice? It turns out that Rameau's theories are sort of turn out to be the background on which all earlier theory depends, namely the the establishment of the diatonic semitone, diatonic genus of music of the ancient Greeks comes from this fundamental bass succession by fifths. Okay, so let's just point out also that we have now derived all the important consonances and dissonances that we need. What am I talking about? Well, in a fundamental sound, let me see if I can find the example I'm looking for. No. In a fundamental sound, there are octaves of each note, and between we'll go back to this example here. We get the major third, the minor third, the fifth. He doesn't notate it here, but the fourth. We get the minor sixth. All of those consonances. Oh, and then between the G and the octave of the E, we get the major sixth. So we've got all of the consonances, fifth, fourth, both thirds, and both sixths, arising from the perfect chord. Well, so much for the consonances, but what about the dissonances? Well, it turns out the dissonances are what connect the consonances, and they are all basically seconds. So we've got the semitone connects the major third to the fourth. The major tone connects the fifth to the major sixth. The minor tone connects the no, I'm sorry, I said that wrong. The major tone connects the fourth to the fifth, and the minor tone connects the fifth to the sixth. And basically all dissonances for Rameau are seconds, or rather sevenths. We'll get back to that a little bit later on because it's important for his theory of dissonance. But let's just take stock for a minute here and realize that we have generated the entire, all the intervals we need in diatonic music from this kind of fundamental note of C, and looking at the harmonic sounds also of its first overtone. That's a different tone, namely G. So from that, we can get all the consonances and dissonances. And then if we want to find those commas and things, well, we could just find the differences between the dissonances. So the difference between the major tone and the minor tone is the syntonic comma, and so forth. Now, the Rameau believes that the ear can't really hear those little intervals like the comma and the quarter tone. The ear does not perceive them because they are derived only kind of as the third order from the fundamental bass. So all of our hearing is based on fundamental succession for Rameau. So even if we just hear this melody, si, ut, re, mi, our ear gives sense to that because underneath it, we're hearing this fundamental succession. Si, ut, re, mi. We always hear harmonically first. And this is Rameau's principle that harmony gives rise to melody. Okay, well, obviously music isn't just made up of tetrachords. We have a bit more of the scale to go. So Rameau gives us the scale this way. Now, this is not the C major scale. So how can we make sense of this? Let's take a look at some math again. We've got our fundamental succession of C, which is 1, and G, which is now 3 in the kind of new system. Well, if we want to go further, we have to turn to Rameau's use of the arithmetic series. So we don't just go in one direction, namely upwards. We can also go in the other direction. And we can look at F as a fundamental sound. And that now is going to be 1/3. Notice that we have flipped from where we were before. Before, the harmonic side, namely proceeding upwards by fifths, was given by fractions. And the arithmetic side, proceeding downward by fifths, was given by whole numbers. We've now flipped that, and that's because of that reciprocal relationship thing. So it doesn't really matter. We still think of C as the fundamental tone, and now we're going to have notes on either side proceeding by fifths. So the lower fifth is going to be given by 1/3, the upper fifth is going to be given by 3. And you could think of that as frequency or whatever, if it bothers you that this is different from the way it was before. All right, well, that's a little, kind of complicated because now we've got fractions again. So let's just, for convenience sake, multiply everything in this proportion by 3. Right? And what that is going to do, remember multiplied by 3 is moving up by fifth, is now we're going to be looking at G major. G major is going to be 3. That's going to be our fundamental tone. Its upper fifth is going to be 9. That's going to be the dominant, or the upper fifth. And then below, we're going to have the lower fifth, or the subdominant, which is downward fifth. And that's going to be given by C, which is 1. So now we've multiplied everything by 3 as a mathematical convenience. So for the rest of the book, everything's going to be in G major, which is 3 as the fundamental sound. And that's going to simplify some of the mathematics as we look at these calculations and derive the rest of the scale. So by adding the third fundamental sound on the lower fifth, which Rameau calls the subdominant, the subdominant, you can get the entire major scale. So let's take a look at the first sort of diatonic tetrachord that we had before. Remember now we're in the key of G. So we've got the principal sound is G, son principal, and that's going to be 3. We have this leading tone below it. Rameau's term is the note sensible, F sharp. And this little scale segment, F sharp, G, A, B, derives from this fundamental progression that we saw before of the dominant moving to the tonic. Dominant moving to tonic is the cadence parfaite, the perfect cadence, okay? So for Rameau, anytime the fundamental succession moves from scale degree 5 to scale degree 1, that's going to be a perfect cadence, okay? And there's our sort of limit is that B. Now to get the C, we have to add a fundamental sound of C, which is the lower fifth of G. You see here, he calls that the subdominant. and we can move C over C, D over G, and that is what Rameau calls an imperfect cadence, okay? This terminology, don't get confused. It is not the same as modern terminology. Now, when we talk about perfect cadence, we usually mean that it has scale degree 1 on top. And when we say an imperfect cadence, we usually mean it has scale degree 3 on top, or sometimes scale degree 5. That's not what we're talking about here. It has nothing to do with melodic position or even what notes in the bass. It's a fundamental succession from the subdominant to the tonic. It's what in modern terms we might call a plagal motion, okay, or a plagal cadence. So we've got C over C, D over G, and we can keep progressing, but here's where we hit the limit. We can go up to E again over C. All right, all is well. You notice here what we've done is we've got two conjunct tetrachords, to talk in Greek terms again. We've got a series of perfect cadences in G, and then an alternation of G and C. So we have gone from scale degree 7 to scale degree 1, 2, 3, 4, 5, 6. Now here is where a problem arises. If we can only move by fifths, how do we get from scale degree 6 to scale degree 7? We cannot. This is a serious problem for the harmonic derivation of the major mode. Now, at this point, you might be thinking, while Rameau's theory is stupid or short-sighted, doesn't Rameau know that the major scale doesn't stop on scale degree 6? Yeah, he knows that. He's actually a pretty good composer. And so he comes up with all kinds of reasons why this has been historically true. First off, he points out that the Greeks always sort of separated their disjunct tetrachords. So we've got two conjunct tetrachords, F sharp up to B, and then B up to E, and then we would have a disjunction, right? So there, he's basically pointing out, well, the ancient Greeks knew about this problem that arose in fundamental bass theory, only they didn't have the kind of theoretical wherewithal to describe it accurately. Secondly, he points out, yeah, well, this is the hexachord, right? Maybe this is why the hexachord only goes up to A and not further. All right, so he's finding all kinds of historical justification, and he points out that this is where parallels arise and tuning problems. It's difficult to sing 3 tones in a row. That's why he writes, 3 tones in a row, which would occur between the C and the F sharp. It's very difficult to sing that in tune. And the reason is there's this disconnect in our brain, because again, all hearing is fundamentally harmonic, a disconnect between the note C, which generates this E, and the note D, which generates this F sharp. They're not connected the way they should be by this extra note G in between, which would allow for a smooth connection. Another way to think about that contrapuntally, there are no common tones between the chord on C and the chord on D. And as you know from trying to do counterpoint at various times in your life, a lack of common tones makes things very hard. It often gives rise to parallels. You have to treat this with great caution. So there's another example of the fundamental bass being behind kind of normal aspects of musical practice. Namely, it's difficult to sing a melodic tritone in tune. So ut, re, mi, fa. It's hard to sing that well. Even I have to sort of think about it as I do it, according to Rameau, right? It's also easy to fall into contrapuntal errors there. It turns out that lack of common tones, lack of connection, as Rameau would call it, gives rise to bad counterpoint. So the only way that he can justify this is either to introduce dissonance, which we'll talk about in a little bit, probably in the next video, or to form a kind of cadence. For instance, you could imagine a cadence on C, and then you just start over on the D from there. And your mind, having given this kind of cadential rounding off of the phrase, is able to sort of restart and forget what you were imagining before. So that's kind of the only justification Rameau can give for a fundamental bass moving by step. But then he points out, well, why do parallel fifths sound bad? Why do parallel octaves sound bad? It's something that we all struggle with, right? Because you're told from your sort of first day of counterpoint lessons, well, you can't have parallel fifths and octaves, right? For Rameau, the reason is because the fundamental bass succession underlying those lacks a connection. It's not moving by perfect fifth, right? There's no G in the middle, so you could have a C and a G moving to a D and an A, and that's bad because our mind is hearing that as a fundamental succession that's not moving correctly. And again, all hearing, all musical perception is harmonic, even if we don't know how to describe that. One last thing to point out, there is a tuning discrepancy that arises here as well. This D has as one of its generated tones an A, right? The A is 27 because it's a fifth above the D, which is 9. Okay, so 27. But the C has as some of its tones the E and the G and the C, of course, itself. And these are out of tune with this A. They don't make pure thirds with the A, right? This is something we've talked about with respect to just intonation. You can't get through a whole octave in perfect tune because there is this sort of discrepancy that arises between the A that would be purely in tune with the C and the E of the C major chord, and the A that would be perfectly in tune with the D major chord, to put it in the terms that we're looking at here. So there's this lack of good tuning, which is yet another reason why fundamental bass progression sort of underlies all musical thinking. He talks about the minor mode as well, but in the interest of time, I think we will table that discussion for now. Okay, so we have now established the diatonic genus of music as being a fundamental succession in the bass of motion by fifths. Very well. Let's talk about one last aspect of this before we move on to the other two genres of music, namely chromatic and then harmonic music. One thing that's important is temperament. So again, this is the tuning problem I was just describing with bad tuning between scale degrees 6 and 7. So one way to fix that is to, instead of going to sharp 7, to change the mode. So now we go from this E here to F natural, and now we would be thinking of C as the tonic, with G and F as its upper and lower dominants, upper and lower fifths. And then we could sort of keep progressing up like that. But then at this point, we would need to switch to F. So Rameau's imagining a kind of infinite diatonic progression that is constantly modulating flatward, which would give rise to a scale that could sort of keep going. But it would never, you can never, with good tuning, again, reach the tonic. You'll never get back to the original sol, because this sol marked by the letter A, this G rather, marked by the letter A, sorry for all the confusing terminology, is differently tuned from the one we started on, right, in just intonation, because we have now derived it as the fifth above C as the tonic rather than as the root above G. Okay, and because of that, we are never able to close the loop without temperament, except that Rameau points out the ear naturally tempers all these intervals. And so temperament is sort of a result of natural human hearing. So temperament then is necessary, according to Rameau. It's necessary because we do it anyway by nature. Here's a really important example for Rameau. This is the same melody written twice. The first example is all diatonic intervals except for this motion from C to C sharp, which makes it the hardest part to sing. La, 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 la. It's hard to get the tuning right of that. And Rameau suggests that the reason I can sing that is because I'm imagining these sort of understandable diatonic progressions by fifths. The one chromatic thing comes from a fundamental bass progression by third. And we'll see later that Rameau uses that to derive the chromatic genus. So underlying that singing of that melody is this kind of simple bass line. La, 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 la. And I can also write the notes as enharmonic equivalents, imagining kind of this other fundamental bass line, and now it's extremely difficult to sing. Okay, because all the things that were diatonic intervals are now chromatic intervals or enharmonic intervals, and they're considerably more difficult to sing correctly. So for instance, just to take the first three notes, it's easy to think of la, 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 and that's a diatonic semitone. And now I'm going to think of them as chromatic semitones over a G sharp chord. La, la, la. And these are, of course, in just intonation, different intervals, but the voice is able to adjust differently based on the different fundamental bass successions. So again, fundamental bass hearing generates everything else. All musical perception is based on hearing the fundamental bass. Now this thing that was a chromatic interval from C to C sharp, now that's a diatonic interval from B sharp to C sharp. So now that becomes one of the easier parts to sing. La, 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 la. Okay, and then I could move from there to sort of imagining a fundamental bass as the fifth of F sharp. And now I can sing from la, la. Think of that as a diatonic interval. La, la. All right, and then I can think that this D is now going to be generated differently to get me from D to E sharp. So now I'm going to sing an augmented second rather than a minor third. Before it was simple, la, la. And now I'm going to think of the same thing as an augmented second. La, la. And the different context in the fundamental bass colors how we hear the tuning of those notes, even though sonically I'm probably singing exactly the same frequencies for each. And of course, if you're playing on a keyboard instrument, you will play exactly the same frequencies for each because you have the same key is supplying both. And then I'm going to have this weird chromatic motion. Instead of this being F to E, now it's going to be E B sharp to E natural. And that's quite different in terms of how we hear it, right? So you could imagine reharmonizing this little simple melody in a different way, and our ear perceives them entirely differently as pitches. Okay, so where does this leave us with temperament? Well, the ear is going to temper anything it hears anyway, based on what it's hearing in the fundamental bass, according to Rameau. So it can hear an interval as diatonic semitones between C and B, or it can hear the same interval as chromatic semitones between B sharp and B natural. And the difference has to do not with the tuning of the instrument itself or the tuning of the singer, but rather with the context in the fundamental bass. And because of that, temperament is natural, and it doesn't matter. It does not matter what kind of pure tuning you use, because for Rameau, the pure tuning is all in your head. Your ear will adjust to whatever it hears. Okay, so that's why in this book, contrary to his earlier practice and contrary to the practice of everyone else writing music in the early 18th century, Rameau adopts equal temperament as the best solution. Why? Not because he liked equal temperament per se. It's because he believed strongly that the ear hears using harmonic hearing based on the fundamental bass. As a result, the ear can adjust to anything. And so you might as well use the simplest temperament that allows you to play in the most keys, because it doesn't matter that it's a little out of tune here and there, because tuning is not actually a function of just hearing actual frequencies hit the eardrum and then deciding whether or not it's in tune. No, it's more a function of the relationship of a sound received by the listener to what the listener is perceiving in the fundamental bass. So that wraps up our sort of introduction. It's Rameau sort of ends the first half of the book there. That basically gets us through chapters 7 and 8 of Génération Harmonique. So in the next video, we'll talk about the introduction of dissonance, which allows for a sort of rethinking of the scale. The theory of the double use of the dissonance on the subdominant degree, which is probably the thing that most of my students hate the most about Rameau and agree with the least. So I'll try to explain it in a way that makes it appealing and worthwhile. And then lastly, how you might apply fundamental bass to composition. Oh, and I skipped also the derivation of chromatic and harmonic genres of music from other fundamental bass successions. So I think the next video will be a little shorter, but this should give you plenty to chew on as you think about Rameau. Hope you enjoyed it. Of course, always, as always, email me if you have any questions. Bye.